transform a primal LP into its dual LP, it must first be in a standard form. So for a maximization problem, it means that all the constraints must be less than or equal to. So these two must be transformed. So we multiply both sides by -1. So we now have -1 minus y3 minus y4 less than or equal to 3. Negative y2 minus y3 less than or equal to -2. And we have negative 2y4 less than or equal to -2. Now, to make a dual problem, a maximization problem becomes a minimization problem, and the right-hand side of the constraints becomes the coefficients of the variables. So you'll end up with 3 variables and 4 constraints. So you end up with 3x1 minus 2x2 minus 2x3. So each variable corresponds to a constraint in the dual. So if you sort of imagine these constraints like a matrix, it's just a transformation. So with the primal constraints defining what variable it is. So you have the minimization, so you have constraints become, this constraint will become -x1. Now there are no other y1s, so that corresponds to this one up here, becomes less than, because it's transformation, it now becomes greater than or equal to -4. This will now be with this one. So because it's in the second constraint, it's now -x2 be greater than or equal to -4 as well, because it corresponds to this one. So now we're here, x1 minus x2 from here, greater than or equal to -6. And then for the last one, it's -2y3, because it's the third constraint, greater than or equal, sorry, that's x3 greater than or equal to 4. So this is now your dual LP. Given the optimal solution to the primal LP is this, how can we use complementary slackness to solve the dual LP? So we let S be the slack variable for the primal LP constraints, because it's a maximum problem, and the same we use E for the excess variables for the dual problem. So complementary slackness says the solution to a primal LP is optimal, then the dual solution will be optimal if and only if the primal variable multiplied by its dual constraint equals 0, and the primal constraint optimized by its dual variable will equal 0. So in layman's terms, so x1 times s1 equals 0, and y1 times e1 equals 0. So to do this, what we do is, given what we have, we substitute these given variables into the primal LP, which will give us z equals 0 minus 4 times 2 minus 0 minus 4 times 1 equals negative 12. Okay. And we substitute these variables into the primal LP's constraints. So y1, which will give us 0 minus 0 plus 1 is less than or equal to 3. Negative 2 minus 0 less than or equal to negative 2. And negative 2 times 1 is less than or equal to negative 2. So these are solved to equality. So that means that S, there is no slack variable, so S equals 0. So 1 is obviously not equal to 3. That means that there must be a slack variable. So from here, we go, there must be a slack variable, so S1 must be greater than or equal to 0. And since S1 times X1 must equal 0, therefore X1 equals 0. Okay. And then because we have the optimal solution here, we know that for y2 equals 2, we know that y2 by e2 has to equal 0. We know y2 is greater than 0, therefore e2 must equal 0. The same is true for y4. So y4 by e4 equals 0. y4 must be greater than 0, therefore e4 equals 0. So using what we have, and we can then go back to the corresponding constraints of the dual problem up here. So that's constraint 2. So it's negative x2 equals negative 4. Because they have no excess, it's an equal sign. And constraint 4 is negative x1 equals, no, negative x1, sorry, minus 2x3 equals negative 4. So this is very straightforward, which gives us x2 equals 4. We already have the value of x1 from up here equals 0. So 0 minus 2x3 equals negative 4. So x3 equals 2. Now, just to double check these and make sure we're all right, we substitute these variables into the objective function of the dual LP, which will give us minus 4, 2 times 2, 0 minus 8 minus 4 equals minus 12. So W equals Z. We have reached the same point, which means that the optimal value for the dual LP is 0, 4, and 2.